Okay, so we're going to continue this question. Okay, so we found the reaction at point C. Next, we need to find the reaction at point A. Okay, so I'm going to copy this diagram over here. Okay, so we know that over here the RC is pushing in at 157.92 times 10 to the power 3 Newton. And I'm going to draw my transformation X, Y, rotation in Z. And now D, at point D, I'm going to assume dx is going this way. Right? Now you know why I made that assumption, right? It's because of this theory of talking you guys, right? It has to be pushing outwards. Okay. So then I start calculating. Okay. So I'm going to apply static analysis to determine reaction at point D now. Okay. So it's static analysis. Summation of forces in the x direction is equal to 0. Positive is going to the right. So minus dx minus twice 75 times 10 to the power 3 plus twice 200 times 10 to the power 3 and then minus 157.92 times 10 to the power 3. The whole thing is equal to 0. Right. So minus dx is equal to 2 times by 75, 2 times 75 power 3. Not 200, 100, sorry. Okay, plus minus by twice times 100 power 3 plus by 157.92 power 3. So I got 107. Okay, I got 107.92 times 10 to the power 3 Newton. And it's minus dx. So the right value, so dx should be equal to minus 107.92 times 10 to the power 3 Newton. Right. So I got my direction wrong. Okay, so the direction. No, when you do structure analysis, when the direction is wrong, don't wipe out. Okay, just cancel and put this. This is the right direction. Okay, so dx is equal to 107.92, and this is the direction. Okay, so if you want to clarify the direction, or your answer can be dx equal to 107.92 times 10 to the power 3 Newton, and you write in the correct direction. Okay, that way. Okay. So the next thing we're going to calculate is we're going to calculate the stresses, the average stress applied in each section. Okay, the average. So from that, okay, I'm going to use this diagram over here. Okay, you can visualize better. So our analysis, we did this, right? We have a fix at D, we remove support at C, and the support at C we got is what? 157.92. Yeah, 157.92 times 10 to the power 3 Newton. Okay. So we are going to calculate that the stresses of AD right? So stress of AD is going to see the 75, okay? It's going to see the 100, it's going to see the 157.92. Now, you will not need to consider the stresses at point D, okay? So down here, no need to consider, okay, I'm going to write down here, sorry, no need to consider the reaction at point D. Okay, and we calculate the reaction at point D, but you don't need to consider that. Okay, because if you consider them, means you have to remove the load. Okay, so we just keep the fixture at point D over there. Okay, so what we see now, the stresses at AD is equal to, so it's going to see twice the 275 forces. Then it's going to see the twice of the 100 in tension. Then it's going to see the 157.92 times 10 to the power 3. And then you divide by the cross-sectional area. So our cross-sectional area is pi multiplied by 0.025 squared. So this will be equal to minus twice times 75 power 3 plus by twice times 100 power 3 minus 157.92 power 3 divided by shift pi divided by 0.025 squared. So I have minus 54.9 63, okay, times 10 to the power 6 Pascal is in compression. Then we calculate the stresses on AB. So stresses on AB, it will not see the twice 75, it will see the twice of the 100. And then minus 175.92. Okay. Then divide by pi r squared. The radius is 0.01. 0.01 squared. Okay, so 2. So it's equal to tension. Now it's positive 133.945 times 10 to the power 6 Pascal. And finally, the reaction at BC. Okay, so reaction at BC, it only sees the 157.92. So it's minus 157.92 because it's compression. Divide by pi 0.025 squared. I do apologize for my background noise because my neighbor is cutting his lawn and he's not cut his lawn for the past 3 weeks. Okay, minus 80.428 times 10 to the power 6 Pascal. Okay, so these are the stresses acting in each section. Okay, so if we were to compare the answer, I believe it's the same, right? They got 80, 134, 55. They did not put in the sign. There's a sign involved. Okay, so 55, 134, and 80. So 54, which is close, 134, yep, 80. Okay, so the answer is exactly the same. So what we have done is opposite to what the book has done, or the solution manual. Okay, and the frustrating thing about the solution manual, they just give you this number. Okay, we have this, we have this, and we have this, sort it out. Okay, at least down here, okay, I explain what is going on, or we explain what is going on down here. Okay, so this is how I will use the solution manual. I'll not follow their procedure, okay, I'll follow the procedure that I teach, okay, and then your answer should be the same, okay. And I hope that this is I think the objective is I want to show you how to make use of the solution manual, more important thing than anything else. Okay, so that's it for statically indeterminate structure. It's pretty straightforward. The only thing that you have to consider is what section to use, how to divide your section, and the critical part when you put in a redundant load, right? For this case, for this example, it happened to when we put in the redundant load, right? It happened to we also analyze 3 sections because of the change in geometry and change in material. The previous example, when we put in the redundant load, we only need to divide into 2 sections. When it's the applied load, you have to divide into 4 sections. So these are the key things that you have to take note, okay? And yeah, the procedure in terms of tension, compression is pretty straightforward over here, okay? So the next topic that I'm going to introduce is not any more difficult. The approach is still the same, okay? But now the stresses is induced by heat, okay? So we are going to go to the next section. Yeah, we are going to look at thermal stresses. I'm going to define 2 statements, okay? And yeah, this statement that I'm going to make is because of the amount of questions that I've solved, and I've come to this conclusion. Okay, so you have to take note on this condition. So when there's a temperature increase, okay, the change in length will increase. That's obvious. Okay. However, the stresses induced is in compression. Some of you like, hey, what does this mean? Okay. So when there's a temperature increase, right, your length will increase, right? But you're going to induce what? Compressive stresses. Okay. Bear with me, okay? And I will show you why. And likewise, when there is a reduction in temperature, right? The length will decrease, resulting in tensile stresses. Some of you like, hey, this does not make sense. Okay, you reduce the length, it should be you should be in compression. Yes or no? Okay. Now this is very unique for temperature change. Okay, that's why if you look at in Canada, we have those overhanging cables, right, where we carry our electricity, right? And I still remember in the year 2013 or 2014, you have heavy snow and rain and freezing rain again, and then all this effect, and then the temperature dropped to -20, and then our cables break, okay, because of twofold: the load of the ice and also the temperature went down very low, okay, and then we